Hi, we are the L.U.N.A team and we are going to present our proposed solution for the NANOSTAR challenge. Let me start with a brief overview of our team. The L.U.N.A team is composed of 5 students, all of which are currently enrolled in the Master in Aeronautical Engineering at Universidad Carlos III de Madrid, and we all have Spanish nationality. Regarding roles, we have Javier Bel Díaz, our thermal engineer, Javier Cortina Fernández, our electric power and telecommunications engineer, Enrique Díaz Arenas, our structural engineer and mission analyst, Manuel Gavilán Herrera, our propulsion and ATCS engineer, and myself, Inés Gordo Esteban, as project manager. I will now throw some data about the nanosatellite industry and its relation to the academic sector. In 2018, 72 nanosatellites were launched by universities around the globe, 12 of which were actually launched by European universities. However, one big difference between most of these missions and NANOSTAR is that most of them are focused on operations around the Earth. In this sense, the most clear precursor of the NANOSTAR challenge is the NASA Lunar IceCube program. Similar to NANOSTAR, this program is also part of a public-private partnership. It is led by a university, and its main objective is also the location of water and ice deposits in the Moon. Just for reference, this program is scheduled to launch in 2020. Now I will give a more technical overview of our project. The operation phase of the project is subdivided into 5 different legs, as you can see here. We have considered the launch, any parking operations in GTO prior to initiating the transfer, the Earth-Moon transfer, the Moon flyby, which is where we must gather all science data, and the Earth return, which includes the transmission of our data back to Earth. Also, here you can see the product tree of our satellite. We have 2 main segments, a space one and a ground one, and inside each of them we have different subsystems which shall be later explained more in depth by my colleagues. In a similar way to the product tree, you can observe here the specification tree of our project, which highlights the dependencies between our requirements. It features 3 different levels: the mission level, the system level, and the subsystem level. The mission and system levels include the requirements provided by the customer, and the subsystem level includes requirements which are team-derived for each subsystem based on the previous ones. We considered several categories for the requirements depending on their character. Also, aside from the specification tree, we compiled more detailed tables like the one included, featuring more information, like the verification means and the rationale, in order to be able to better monitor the requirements during the project. With this said, we shall now proceed to explain more in depth the characteristics of our proposed design.
Let us start with the mission analysis. The picture that you can see here is the actual model of the trajectory after solving the corresponding orbital mechanics problem. The satellite starts its journey from a high inclination GTO in order to fly over the poles of the Moon. A free return trajectory is planned. For this, the transfer ellipse is designed to intercept the Moon orbit, benefit from its gravity pull, and come back to GTO. Several impulsive burns are planned at the GTO perigee in order to minimize gravity losses in each maneuver. Under these conditions, a cumulative delta V of 0.7 km per second is needed for the maneuvers at each perigee of the displayed ellipses, as shown in the graph. Then, a high margin of 25% is applied to this preliminary calculation to account for possible in-flight maneuvers and losses.
Regarding the propulsion subsystem, chemical propulsion using bipropellant thruster and fuel emission electric propulsion have been traded off. The outcome was that despite the reduced mass and volume, the design mission does not have sufficiently large delta V requirements to choose electric propulsion, due to the large power requirement it involves, the negative impact on the satellite due to contamination and sputtering, the radiation problem coming from excessive radiation due to the large residence time in vanillate belts, and the oversizing of thermal component as absorbed and increased with material age. Therefore, the primary propulsion system will be based on chemical propulsion. In particular, given that multiple maneuvers are required, we are limited to using liquid propulsion. More specifically, a mixture of ethanol and hydrogen peroxide has been selected given its size-specific impulse of 315 seconds. As it was mentioned in the mission analysis, 4 burns are to be performed at the GTO perigee, which sets, taking into account proper margins, a delta V of 225 meters per second in each burning maneuver. This implies, given the requirement in terms of thrust, a burning time of 770 seconds at 4 newtons. This way, though present, gravity losses, which were about 20% for the case of single bar transfer, are minimized. We can also see the sizing of the bipropellant chemical propulsion system, including propellant, tanks, pressurizer, and thruster mass. Regarding the ADCS, dual spin was discarded because despite having increased lifetime, reduced cost, and enhanced stability, it is mechanically complex, has a poor power efficiency, and has limited maneuverability and pointing accuracy. Therefore, a 3-axis stabilized spacecraft shall be used. Here we can see the satellite ADCS mode architecture, in which we shall highlight the sign and nadir mode, where payload operations shall occur, and the different connection between modes, both in nominal and failure detection condition. We shall also mention the safe mode, in which the satellite may enter at any point of the mission. Then, we have the angular momentum change through the mission, being solar radiation the most significant environmental torque. To ensure control actuators having a control authority to balance thrust misalignment, the satellite is spun along thrust direction during the burning maneuver. Finally, we see the ADCS architecture, composed of 3 reaction wheels, a reaction control system made of 4 nitrogen cold gas thrusters, 4 sun sensors, 2 star trackers, an inertial measurement unit made of 3 accelerometers and 3 gyroscopes, and finally 3 PID controllers to control attitude in 3 axes and an extended Kalman filter.
Besides the main payload, we have designed the satellite to carry an additional camera, which will capture data in the infrared spectrum. We have chosen an infrared camera because ICE has a strong absorbency in this range of wavelengths. Regarding the payload itself, it will capture 50 megabits of data and will have similar characteristics to the other payload. 5 different frequency bands were available to choose from. A trade-off analysis was made where it was decided that the most convenient one was the S-band. The main designing factors were the interference with other signals and the capability of HISA to receive and transmit data in this band. Regarding the data to be transmitted, it was divided in 2 categories. The first one corresponds to the telemetry, tracking and control, which is 1 kilobyte of data transmitted over 10 seconds. The second one is the scientific data, which is 25 megabytes that will be recorded during the flyby. If this data is transmitted on the way back over a period of 3 days, the bitrate will be similar for both types of communications and will unify the transmission characteristics. The antenna selected for the communication is the NANOCOM ANT2000 from GomSpace. This antenna was selected because it operates in the S-band, it has a compact size, and it has shielded electronics. Regarding the ground segment, we will rely on S-Track, which is ESA's tracking station network. Due to the geometry of our mission, the ground stations that we will rely on are the Svalbard ground station when the satellite is over the North Hemisphere, and the Troll station in Antarctica when the satellite is over the Southern Hemisphere. The first thing to know in order to size the primary power source is the power requirements in the different modes of the mission. The most power demanding one is the science mode, which with a margin of 35% yields a total power input of 29.3 watts. According to Angrist, there is a relationship between the most appropriate power source knowing the power demand and the mission duration. In our case, it lies between the fuel cells and the solar arrays, and after a trade-off analysis it was determined that the most appropriate one was the solar arrays. The material chosen for the solar arrays is a multi-junction of gallium arsenide. This material was selected because it absorbs energy over a wider wavelength range, which highly increases its efficiency up to 28%. The solar arrays were designed for the worst case scenario, which is the condition where the sunlight only hits one side of the satellite. For this condition, taking into account a 81% efficiency, a 20-degree maximum deviation, and an effective area 90%, the solar arrays must have an area of 1,120 square centimeters. Half of this area will be attached to the satellite, and the other half will be deployable. This setup is repeated in 4 sides of the satellite. The material selected for the batteries was nickel and lithium, since they have a better performance than other materials and they are widely used in the industry. The batteries were sized to power the satellite in 2 different conditions. The first one is during an eclipse in the perigee, when the impulsive maneuver would take place. Considering that power requirement and the eclipse duration of 25 minutes, the batteries would need to have a capacity of 15 watts-hour. The second condition is to power the satellite's safe mode for 12 hours without the use of the solar arrays. Even though the power requirement is lower, the condition is more restrictive due to the longer duration. The capacity required for this condition is 122.4 watts-hour, which can be fulfilled with 80% of the capacity of 2 nanopower VPX from GomSpace.
When it comes to structural design, we shall mention that the primary structure is made of aluminum 6061 and it has an overall weight of 1.2 kilograms. The dimensions are 20 x 20 x 30 centimeters plus the payload, which is attached outside the primary structure. We can see here all components. The 2 cameras and the antenna are outside. Below them, we find the 2 batteries, the electronics, the inertial measuring unit, and 1 star tracker plus an attitude control thruster. Below, the reaction wheels and sun sensors, which can be also embedded in the solar arrays. And finally, the tanks, main thruster, and the rest of attitude control thrusters. In addition to this, several configurations are defined to check the center of gravity, which is displayed in green, and the inertia. This is the launch one, and just as an illustration, this is the empty tanks and full deployment configuration. The overall weight of the satellite is less than 14 kilograms. Now, if we focus a little bit more in some analysis of these parts, we might want to check the tanks. This is the oxidizer tank, which is the biggest of the two, and we can see that being made of titanium, it weighs 0.3 kilograms, and still it resists the pressure of 33 bars. A high mass margin is set for maturity and filling lines consideration. Then, another interesting point is the model analysis. The FEM models for the satellite and a solar panel are shown here with their first modes. The satellite is clamped from below, and the solar panel is modeled allowing rotation at its hinge. We can see that the bending and torsion behavior of both structures are well characterized by these models. Moreover, these allow us having a value for the frequencies that we must take care of to avoid resonance of our nanosatellite.
The thermal control subsystem is presented now. The goal of this subsystem is to maintain the temperature of the different components of the spacecraft within the ranges specified in their requirements, and in all phases of the mission. Regarding the thermal environment, the spacecraft is orbiting in vacuum. Therefore, there is no outside convection or conduction. Radiation is the only mean of heat exchange with the environment. Inside the spacecraft, conduction and radiation between the different parts are the relevant mechanisms. Moreover, the external thermal loads that the satellite will have to face are the solar irradiance, which depends on the distance from the Sun, and at the distances that are treated in this preliminary design, the Sun can be considered as a point source for a thermal control analysis. The planetary albedo, for which the bodies that must be taken into account are the Earth and the Moon, although it is worth mentioning that the contribution of the Moon albedo is very small. The planetary infrared, as celestial bodies emit some thermal radiation into space, typically in the infrared band, and the background space, which can be considered negligible. This thermal environment may cause inadmissible temperatures in certain components of the spacecraft, so an essential issue is to gather all the thermal requirements from the different components. Two types of thermal ranges appear, the operating range and the non-operating one, and here a table is presented with the thermal requirements for each component. Once the thermal ranges allowed to the different components are known, the thermal analyses are now shown. With this purpose, the ESA-TAN tool has been used. In order to carry out the required simulations, it is necessary to model the geometry of the spacecraft, introduce all the materials, optical properties and boundary conditions that come into play, as well as to propose the most critical thermal scenarios. This, together with the modeling of the conductive interfaces and the contact zones between the different elements, is necessary when solving each thermal case. Regarding the optical properties and boundary conditions, these are the main ones used, where it has been considered in the boundary conditions that a proper percentage of the power consumed by these equipments is dissipated by heat. These are some pictures of the geometry model created, and these others are depicting the different conductive interfaces in yellow and contact zones in orange between different components. Then, an essential part of the thermal design is the selection of the worst-case scenarios that the satellite can find during the mission, since they are the ones that must be taken into account when carrying out the thermal design. Two main scenarios have been considered, which are the candidates for the worst-case cold and the worst-case hot scenarios. Both are here represented. For the coldest case, it is assumed a polar orbit in which the spacecraft is in an eclipse that occurs around the perigee and with the apogee a little beyond the Moon, in such a way that the spacecraft can correctly perform the required flyby. It must also be said that during the eclipse, the main payloads are non-operating, while the batteries do. Regarding the hottest case, it has been considered an orbit that passes close to the Moon without eclipses and with the closest distance from the Sun of the entire mission. In this scenario, the main payloads are operating when performing the flyby. Finally, the results obtained are now presented. This is the general visualization of the temperature evolution along the orbit for the components of the spacecraft. First, for the worst case cold scenario, and then for the worst case hot scenario. In addition, the temperature evolutions with time obtained from the simulations. Reminding the thermal requirements exposed previously, it can be checked that the temperature of each element is within its corresponding thermal range throughout the whole mission. So the main thermal objective is fulfilled. Finally, it is worth mentioning that passive control has been preferred to the active one when it comes to tackling the thermal design, since the first one consists of introducing paint or texture of the surfaces to change the effective values of the solar absorptivity and infrared emissivity, while the second option involves increasing significantly the mass budget by introducing elements that control the temperature.
Finally, we shall take a look at some of the risks that are present in the mission. These are just few of them. Regarding the management part, a conflict between the different stakeholders, budget issues, and unexpected changes can cause delays and increase the cost of the project. Due to this, good management practices shall be adopted and the flow of information between stakeholders must be continuous and complete. From a technical standpoint, manufacturing and certification can pose some delays and cost increase. Most importantly, conscious analysis must be performed to ensure compatibility of the satellite with the launcher vibratory environment. Finally, lack of maturity and especially redundancy must be taken care of to ensure the mission success. With this, we conclude our presentation. Thank you for your time and attention.